Yeah, thanks for the introduction. Was so great actually that I can just skip the title slide and get right into it. Yeah, NAPS is for deep learning, but why do we need something specifically for deep learning? Why is deep learning different in terms of HPO? And the thing that's different about it, or one of the things, is that the strategy behind deep learning right now is essentially more compute, more data, and you get better results. This is also illustrated by this graphic you see here, where you can see the training compute evolving over time as the years progress. And you see that once deep learning really starts to kick in around 2012 with the success on ImageNet, the rate at which the training requirements are increasing is actually increasing, and pretty much so, right? So these ever-growing resource requirements, they lead to a few questions. For example, isn't HPO too expensive to perform on deep learning? Because in classic machine learning, right, we can even do things like cross-validation, and that's for many deep learning pipelines is just completely out of the picture. Do the HPO tools play nice with the necessary infrastructure that we need to run deep learning at scale, and that the deep learning experts have come up with to deal with this scale? Because as you can see, there's not only an increase in training compute, there's also an increase in interest and research behind things. Can a black box even be trusted, or should we rather rely on our expert that's reading a lot of papers, that knows a lot of things, that talks to Jeff, that looks at Twitter threads and knows all sorts of things? And to address these questions, or these questions whether they motivated us to develop NAPS and come up with an HPO tool that can work for deep learning workflows. One of the main things, of course, are the algorithms that we are researching on, that we're developing. And from the get-go, from the inception, we're tailoring these algorithms to deep learning. For example, we integrate experts' knowledge. So we can make use of whatever Jeff says, we can make use of whatever Twitter thread is going on by letting the expert integrate their knowledge. We open up the black box in several ways, and I'm going to talk about this in more detail. But most importantly, we work with minimal resource requirements for HPO, meaning something like only 5 full trainings of the network, because we can't afford 50, 500, 1,000 runs that you often see in classic machine learning. Yeah, so this is the algorithmic side of things, but also there's a technical side of things, which is playing nice with the deep learning infrastructure. For example, if a network takes 2 weeks to train, we can't afford to do it 5 times, 10 times sequentially. We have to do things in parallel. And this happens so often that we made sure that you need to put the least amount of effort to parallelize using NAPS. Say 0 lines of code change, and you will see that in the hands-on today, I promise. Another technical thing that we're dealing with in deep learning is checkpoint management. Because if you spend a lot of compute, if you spend a lot of money on training your network, you don't want to throw away its weights. And you don't even want to throw away its weights inside the HPO process. You want to continue from these weights. And this checkpoint management can be a pretty tedious thing to do, especially if you're now running an algorithm on this. You have to do it all manually still, like you have to code it manually, right? And we make this as easy as we can. Another thing is that the experts, they don't want to lose control over what's happening, even if they trust the algorithm. They want to look at TensorBoard. They want to see how are the gradient norms evolving over time. Do I need to stop the HPO? Is it all going well? They want to have this live view on things. And that's what we make possible with NAPS as well. So these are the main 2 aspects. So if you want to be sold, then look at these 2. But there's more that I want to highlight here. One being that HPO for deep learning is very much an ongoing research topic. It's actually far from solved, I would say. For foundation models at the largest scales or even at medium scales, I'm not convinced that there's a reasonable algorithm out there yet. And Frank is nodding, so I'm not talking bullshit here. So We're actually working on this. So it's not out there yet, but with NAPS, we're trying to have our algorithms land in the master branch more or less as soon as we develop them, as we publish them, and make them available as fast as possible. Another aspect that's still in research is that in deep learning, there are a lot of specialized components that are very complex. Think, for example, of the architecture, and there are whole subfields of AutoML dealing with just the optimization for specific subcomponents. For example, neural architecture search deals with optimizing just the architecture. And this is also still very much evolving, and we do incorporate this optimization of the architecture, for example, in NAPS as well. But this is still a little bit of an advanced topic. We won't cover it today. I don't think you've heard a lot about neural architecture search at all, or let alone all the other components like optimizer search or things like that. Or let alone the most crazy thing of them all, doing it all together, tuning the architecture, hyperparameters and everything. And if you want to learn a little bit about that aspect, then make sure to listen to Frank's talk tomorrow, where he will go into this in more detail in what he calls Deep Learning 2.0, which in and of itself is a pretty bold claim just from the name, right? So yeah, the last thing I want to highlight here is that deep learning covers a lot of different workflows. I've highlighted already this super ridiculous large scale of things, but of course, there's also, aside from something like a GPT-5 model, there's also these small models that are already in production, where you already have them running and working well. You already have a learning rate that kind of works well, but now maybe you get some additional data and you want to make sure that you still have the right learning rate. And we want to make sure that all these workflows work well with NAPS. Yeah, so let's get back to the algorithms of things, because, well, these are the workhorse of NAPS. These are the workhorse of HPO. In general, I won't cover algorithms in detail here. I'm just going to run you down the main features of the algorithms that you're also going to see in the hands-on in just a few minutes. But again, I recommend you to listen to Frank's talk tomorrow. I think it's the first one, where he will talk about all these algorithms in detail and maybe even show you some benchmarks and stuff to convince you that they are good algorithms. So I already talked about integrating the expert's knowledge a few times, and this is a pretty important point. But importantly, the expert might also be wrong, right? So in our algorithms, we make sure that we can recover from misleading knowledge. For some algorithms, we even prove it. For others, we show it empirically. One other thing that experts tend to do when they optimize models manually is that they monitor the runs. And they can see, okay, this run is unpromising, it doesn't go anywhere, I am just not continuing it. Maybe you've heard this under the umbrella term multi-fidelity optimization already. That's what we're doing as well. I also mentioned parallelization already. And yeah, we do that in 0 lines of code, and you will see that in a second. I've also mentioned that we're still researching for these very big models, and that's something that we're targeting as well, to incorporate scaling behavior, to finally have an algorithm that can work at the very largest scales. Because as I said, there's nothing out there yet that really convinces me. And most importantly of it all, we do all of the above at the same time. And we do it easily. And that's what we're trying to convince you of with the hands-on that's going to start now. So you have a QR code here, you have a tiny URL, you know how this works. We have some instructions up here. We will mainly walk you through this on the Beamer as well. Neeratyoy is going to take over that process, so yeah, have fun with that.
Hi, thanks, Danny. So this is a collab notebook. I will hold on to this slide for a bit longer. I'm assuming most of you will join me in walking along. So the way we'll go about is that I'll just quickly run the basic installations and other things. And at the moments where it will take like 2, 3, 4 minutes to run the trainings, Danny and I will just walk around if you have questions, and That's how we like just stage and segment the talk. But yeah, I'll leave it here for another 10 seconds and then switch to the collab. But if you have questions regarding the working of copying the collab to your drive or something, please feel free to ask as well. So basically, we have this code prepared here to kind of simulate the whole scenario that like if you follow what Danny's main point was, that with the whole idea of minimizing code, I think what we're trying to simulate here is that imagine that you have worked on your task already and you have a deep learning task that is specific to your requirement. In this case, we will go to what we are saying, but what we want to illustrate is that if you have that task existing, which you have obviously customized for your need, you can do HPO with absolutely minimal code and overheads, and that's what we want to simulate here, that the code repo that your task is existing somewhere else, and you technically are not editing it for HPO, but you're kind of still able to wrap HPO around it. To begin with, to simulate the flavor of what's happening, I'm trying to motivate here what black box optimization is. So there are these things called Brownian function, that it's a synthetic function, a two-dimensional thing. And what it ultimately does is it just evaluates some two-dimensional points, observes what the value is, and given like a bunch of observations, predicts like where you should evaluate next, right? Because how you minimize the HPO landscape. I think Joseph earlier talked about the landscape of hyperparameter tuning. So when you have no idea about the actual convexity of the landscape, you kind of treat it as a black box. And what I'm trying to simulate here is that if you have a Brownian-like black box function, if you treat its inputs as hyperparameters, what I want to illustrate is the simplicity of how to just tune it, that if you have a function which takes like the inputs of Brownian and outputs the actual y value of the function, what you can do is just create a search space here with these are values specified by the Brownian domain. And all you need to do is just call this function from neps here, and that's it. So if you run it, I guess for me, I've already run it. So you should see something like this come out super fast. And there are log files which you can see that, okay, they have run and they are kind of finding lower values, which is what the goal is. So this is just to illustrate the overall loop that you need is absolutely simple and trivial. And this is what we'll kind of scale up to an actual deep learning task going forward. So yeah, is that good? People were able to run the basic loop, so that means NEPS is working for you, correct? All right, sweet. Great. So the deep learning task that we have kind of set up is a quite trivial CNN-based multi-class classification where we download MNIST and do a CNN, optimize it using some optimizers, etc. We have code ready for that already. I would recommend you download the data set. And if you execute this cell, this is just to demo what the wrapper of that code is. And the reason I'm focusing on this is that no matter what your deep learning task is, whichever way you write it, ultimately all your scripts end up having this one entry point, right? Like a main function. And you can give it a lot of parameters, arguments, YAML configurations, etc. And they can cover a lot of different properties, like how do you control checkpoints. This is our actual point of interest, but you can also add like other settings and everything. And what I'm trying to say is that this is a general function which is pertaining to your task, which exists, and we are just going to use that off the shelf. So this, in our case, obviously does a simple two-epoch training, and it works. It gives out a lot output. The only caveat for this to work with NEPS is that we need this thing here. So whatever function you're creating should return a minimizing metric. So it could be the training loss. It could be some validation error, depending on your task. In our case, we have classification, so we do validation error here. And that's the only requirement, that your function should return a minimizing metric. Going back to Brownian, why it works with NEPS is that we return one floating value, which is a minimizing metric, and that's all it was needed to kind of wrap an HPO optimizer around it. And if you really want to also just, if you are a deep learner or are familiar with it, this is, I just quickly go through the code of what we are training. It's nothing fancy, it's a standard loop. where you load a data loader. This is like a NN module, a standard PyTorch module that you load. You have a cross entropy loss, set up the optimizer, a cosine annealing learning rate schedule, and then you just train for the epochs, like a very, very standard setup, right? So it's nothing fancy at all. Right. So we are good till now. Any questions? So we have basically downloaded the data, checked if NEPS works, and have a task that we would like to optimize. Maybe I quickly go back to this thing here just to highlight that if you see actually everything here, we have the freedom to completely optimize the hell out of it. Like, we are parameterizing all possible things in the pipeline, and we can technically optimize anything we want. So that's the setup. But okay, now getting to the actual NEPS setup, what we need here are three important things to really make a NEPS HPO run work. First, we need a run pipeline function, which is essentially, if you see here, is a wrapper around your actual task that is coming from some other repo, some other file. We don't really care as long as it can take in the arguments. These two, we'll come back to it later, but are NEP-specific arguments that you need to provide, or as a matter of fact, you can also not provide it, but this is like a general thing which will work for all possible algorithms. And all you can really do is just say, oh yeah, I'll just send a bunch of hyperparameters and that's it. You don't really need to care about specifying what to do there. And you can configure your training for any miscellaneous settings that you want, and it should still be fine. So the core thing being that, okay, I have a run pipeline which is in this signature, function signature, so that NEPS can read it. That's it. Then the next important thing is, okay, I would obviously like a search space to optimize over. And in this case, all I want to say, because I'm giving a demo, I'll just say, yeah, okay, let me tune the learning rate alone. And I obviously set some bounds which are intuitive to me. I say, okay, it'll be a log space optimization, and that's it for now. After that, all you need to do is specify to the NEPS run that, okay, this is the function that I want to optimize over. This is my output directory, so that's quite a standard thing. And then this is the search space. Done. And this is the number of evaluations I want to do as my HPO budget. So for this toy run, I'll just do like 3 evaluations, as you can see here. Are people able to run this cell? Did people? Yeah? Frank? Okay, good. So it's just a demo run of 3 evaluations to show the whole point being like all of this loop kind of like fits in a maximized screen even. And that's the whole point that we're trying to say, that you got in your task from some like outside repo where you have this function which exposes everything. And then you just wrap it, create a search space, and tune it. Done. It technically works. And once it has run, that's not enough, because if you can see, we are not returning anything, which is a typical way of interacting with Python packages and code. That's because everything happens on a file system basis. So this specification of where you want to store results is quite crucial for NEPS, because as Danny will later show as well, for parallelism, that's extremely crucial. But everything you want to know about how your HPO run unfolded, the kind of optimization that went through, happens in that folder directory. So for instance, if you just do this, that you have a status and you just give the output path as an input, it should be able to, oops. Okay. I should have restarted the notebook. But does this line work for you? Yeah, okay, so maybe because my session kind of got corrupted. So I'll try to avoid rerunning stuff, but the outputs are all there. So yeah, so I hope this runs for you. And what do you see? Does anyone want to say what they see? Like, does it show the number of evaluations and the best configuration found? Yeah, so that's the whole key there. And the structure of the output directory is as follows, that you get a total summary files of what the optimization is recording, a results folder which records all the configurations with specific IDs. So in this case, we gave a budget of 3, and each is a different configuration which got recorded. And you can obviously cat and double click and open it if you are on a machine, and you see everything that you've logged there. So that's the essential key, that like the output directory is your complete repo of information of whatever happens in HPO. So neps.run can technically, if you see, be an asynchronous call where you don't need to wait to record what it is returning. That's the other important key thing. And once the run's complete, there's a CSV already dumped, which allows you to kind of load the results, view it, or plot whatever you want, essentially, or diagnose, analyze anything that you want there. And that's the whole broad idea of, OK, as you show this also. So technically, we also log tensor board as well. And this is, I'm doing it post hoc, but technically, if you run this tensor board actually on a machine as well, while this HPO run is going on, you can monitor how individual configurations are progressing over time. And maybe I should just also show some side features, and that is you can, so this loss is ultimately the minimizing metric that you're returning from your function, right? That your HPO algorithm is optimizing over this value. It could be validation error, etc. But what is a cool thing, according to me, is that you can also monitor like how the L2 norm of the weights or the activations are progressing while you're training, so that you can get not just an information on a high level that, okay, this hyperparameter leads to this loss, but you can actually start making sense early on that, is this hyperparameter legitimate in terms of like creating a stable model? Because if I just see the last black box value of, okay, my loss is so and so, my pairwise comparison of hyperparameters may be inadequate. But if I look into model diagnostics of how these hyperparameters are actually training, I get a lot more information, which is what Danny was alluding to when he said, let's open the glass box, or let's look at what's happening and what deep learners want as control. They just don't want a set of hyperparameters that works for them, but they would also like to know if those hyperparameters are actually leading to more stable training and better models. And also we have some features. This is just one hyperparameter for 3 models, so it looks pretty naive. But the whole point is that if you have more runs, these lines will show up in thickness, will tell you that which hyperparameters have been found more often to be a better loss value as well. So for example, this hyperparameter, this learning rate leads us to the lowest loss in the 3 evaluations we've seen. So imagine a lot of evaluations, and you'll see a more thick density over the best loss seen. Right. Now we will questions, actually. Everyone was able to run this. Can you see the TensorBoard yourself? Play around with it? OK, great. Sweet. So now we will, sorry.
Just to get some clarification, I didn't see the parallel curve in this boss from
Really?
error.
But do you see the TensorBoard, right? Should I come there quickly?
I don't know.
Is there anybody sharing that problem? Like, can I get a show of hands who could see the TensorBoard open up on Colab? All right, so do you see this panel as well with scalars and h-params? Yeah, and does clicking on h-param work? And now can you click on parallel coordinates plot? OK, sweet. So everyone can technically see that, right? OK, sweet. Great. Cool. So that was a very demo run, which kind of just enumerates the feature, to be honest. But now if we try to like, say now we tested our pipeline. So we are bringing in a task that we want to tune. We want to tune using neps, and we just very easily, I would say easily, just could already tune my learning rate for a setup. So it just works of the kind of almost very simply. But now I actually want to tune some more stuff. So what I just do is like, I just add these hyperparameters that I want to tune, and intentionally I chose this just to show that the kind of types we support, float, categorical, integer, etc. And if you run it, this will take about 5 minutes. So this is a point where I think we would just move around a little bit and ask questions. But again, the whole thing is that you just add the hyperparameters you want to do, and you just hit neps.run. And with nothing changed, other than just the fact that your output directory has to be different, because you want to obviously log it elsewhere so that your files don't clash with each other. But that's it. So while it's running, I think we will just quickly walk around and see if there are questions. Yeah? Also. You have a question?
Yes, I did pad performance, but it's still in C Pro code on it.
If you click on here, okay. Does it for the, if you click it? Okay.
It has, but
Yeah.
yes, that part is still false.
Oh, sorry. I should have really restarted the session because now it's just breaking. So, but it's running for, I could try, yeah. I didn't interrupt it.
Meditation and that's unprecious. It's
Yeah, so one interesting thing is that, so I guess I was over prepared for the talk because I ran everything early on, and now TensorBoard sessions are betraying me. But the cool thing is, if you see, I reran it. I don't know if it registered a keyboard interrupt somehow, but I'm rerunning it now, and it begins from like config 2. That's a cool demonstration that like, because of the file system angle I mentioned, the cool thing about Neps is you can just kill it, or even if your processes die, as long as your configuration, as in like this part here is not changing and you're pointing to the same file path, you can rerun the exact same code and it should be able to resume if the budget here is not over yet, you know? And that's, I think, one great feature, which if you think about it, also allows for parallelization super easily. So you can like spawn workers anytime as long as the HPO budget is there. And even if workers die, you don't really lose anything, which is not very, I think it's a good feature. Danny will obviously talk about it more and show things as well. Yeah, if you have a TPU or a CPU, then it'll probably be faster. But yeah, so a couple of questions I was asked. Maybe I can share them. One was, I guess, like the question was, for people who noticed, like, do we always run Bayesian optimization? And that's a very good question, because one thing that I didn't talk about is that we're not actually ever mentioning what to use for HPO optimization here. All you're caring about is, okay, this is the task I want to optimize for. These are the hyperparameters I want to tune, like learning rate, optimizer, choice of optimizer, and then you just run neps. So what's happening? It's a good question. I'll come to it a bit detailed later, but that's how our design goal is, that we go to deep learning practitioners and don't let them necessarily, or give them the option of not having to choose. Because what we do is we have a simple decision tree like thing internally, where we just, given the problem type, choose the exact optimizer that we will apply for you. And that also then feeds back to the entire flow, that you can just sit there with one loop over your actual task and never really change it. And going back to what Danny's point was, that the way we are designing is that all of our latest research will automatically kind of quickly be there available as an optimizer. So we might, if we do something better than our current work, we will provide that to you, and you don't need to change your HPO wrapper, and it will still work and come up with the better optimization. But we will see later also that you, of course, have the control as well, where you can choose the exact optimizer you want to work with and the hyperparameters for that. For example, you can explicitly specify that I want Bayesian optimization, and then you can explicitly also choose that I want so-and-so acquisition function, and etc. But this is to just show the simplicity of and how we are trying to get to the no-code setup mainly. All right, so it took some time, but yeah, it figured out something. It had some loss. Yeah, and now if you see, we do the same thing. We can ask for directly the best configs, and the advantage of having like files like these as well also, for example, these just track the incumbents, like it only updates the best configuration we have seen, means that you can always have scripts running around it, which can pick up the best hyperparameters. And if you want to like pass that hyperparameter to some other pipeline, you can automate that as well in principle. Right. So yeah, and I guess like for people who are doing this correctly as well, there is another TensorBoard which was supposed to work on results HPO, which should have in principle, if you refreshed it, shown you the live learning curves while this was being run. So you could just go back and forth and actually view the trainings that's going on. All right. So what we did in that part, as you saw, was Bayesian optimization. But we know, I mean, at least like, so the thing with Bayesian optimization is that it does not tune the epoch. Like it always evaluates all configurations for some specified budget of epochs, like let's say 10 epochs, 100 epochs. Now, that is super slow if you're trying to evaluate and find your best hyperparameters, right? So there is a lot of research around how you can speed that up. One naive thing, of course, naive in the sense of like algorithmically naive, it's just something you can do, is there's a lot of work on parallel BO and other things, and what Danny will demo, but this is a brief example of how to go about it, is that this is the structure we have already written, right? neps.run, things run. But if I want to parallelize it, what I need to do is just deploy the script multiple times, because all of them, because each execution of the script is a process, and they sync with the path that you're specifying. So it just works. It will just read and synchronize internally, and so you can spawn to up to hundreds of workers. Like we have at least gone up to like 256 workers or something like that, and it just works off the shelf without having to write any extra code, as Danny pointed out. So that is one way of speeding up any run that you have, but it does not take away the problem that each run is still trying to see if my learning rate of 0.01 is better than 0.001 by training for 10 epochs for both of them, right? But we can do better. Research suggests so. And that's where like, oh, this is like a re-illustration of my previous point of how you can resume a run very quickly. But what we want to mainly talk about here is multi-fidelity. One thing that you need to additionally do is actually specify to neps that, okay, here is a fidelity parameter that you have to consider. And that's it. The rest of the thing is exactly the same. All we do is change the output path. And if you see now, if you have run this already, you'll see that it's selected hyperband by itself. And that's the kind of design we're aiming for, that because you introduce the fidelity, and our research, our empirical evaluation so that hyperband can be better than BO under certain speed up conditions, we choose that. And under actually much lesser budget, which is like almost like a little above half the time that it took to run BO, we kind of, I think, if you compare the status of the two runs, the multi-fidelity and the vanilla HPO run, you should see that the multi-fidelity run achieves a better error already in like almost half the budget than BO. Yeah, everyone mostly till here? Cool. So and the other thing is that, like, if you see, they did pick similar hyperparameters nonetheless, but still was able to figure out that I can get to that hyperparameter for much cheaper because of how multi-fidelity or hyperband works. And one quick intuition of hyperband would be like, think of it as me training 10 configurations for one epoch, and I take the top 5 configurations, then train only those top 5 for 2 more epochs to go to 3 epochs. Then I take the top 2 configuration, then train only them for 10 epochs. So what happens is that instead of training each for 10 epochs, I, for net total lower cost, do some hedging and get to a better configuration. And there's a lot of work around it in terms of algorithms. And this is to highlight how NEPS is a bit different when it comes to multi-fidelity compared to BO, is that now you see earlier for BO, it was like config 4, config 5, but now there is an additional ID, and that kind of points to, I can see. It's red. Is that an issue?
Feels like the same problem as yesterday. It's overheating.
But we are good, right?
But it could happen again.
Okay.
So, but it's good. It's all running anyways.
Sweet, sweet. Where was I? Yeah, so what I wanted to point out is that, like, why hyperband-like methods are what we are going for to solve this HPO for deep learning is, think of it this way, that what this means here, if the IDs are like this, is that, like, configuration 5, whatever hyperparameters were sampled at that point, were trained for, let's say, 1 epoch. Then the algorithm figured out that this hyperparameter feels promising, so let's kind of go and train it for another few more epochs. And that's why some of them have this second ID going +1, which is to suggest that you are breaking the complete training of one model down into smaller steps and choosing if you want to continue them or not. And if you, oopsies. And if you see that the checkpoint here, like if you actually do a proper run, you'll see that this checkpoint actually starts from here. And that's why you can gain these speed ups and basically for much cheaper get similar and improve results. Cool. So we basically see that you can speed up using parallelization, you can do some basic multi-fidelity, but can we do more or can we speed up even more? And that's where we go back to one more point from Danny was that expert priors, like, can we give the optimization algorithm already some information that we know of? For example, learning rate. Like there are PyTorch defaults, right? Like why do they exist if you've ever used PyTorch for deep learning that they already put values for learning rate, weight decay, etc. That's just like a general thing which seems to work generally well, right? And when we do an optimization, we just have a uniform search space where we give a bound. But what if we feed that into the algorithm as well? And so we do that by just specifying a default and a confidence value that, okay, I know that this learning rate is good, but I'm not sure how good that is. But I know that Adam W is pretty awesome, so let's just put it a high confidence value. So things like that. And if you run using that now, as you see, similar call, change the output path, it picks up prior band as a searcher because that's an algorithm which can deal with multi-fidelity and some extra input of what a good configuration is. And with a similar runtime, we basically get slightly better performance improvement already. And interestingly, this time we have a very different model size and a learning rate selected for that. And it's all happening with like almost minor changes in code and with the same setup being run. And by the way, the obvious thing is like all of these can be, again, parallelized very simply. So that's the nutshell thing that I wanted to mainly talk about. And what I said earlier, it does not mean that you cannot specify searchers. There's a bunch of algorithms that we already have. And you can even use some other code to figure out like, okay, what hyperparameters they have further if you are into HPO and want to control everything of it. And that's the main thing. And there is a notebook that there exists if you want to play around with NEPs, different optimizers in NEPs and their hyperparameters. We have a learning curve benchmark plugged in there, which will run much, much faster than training an actual model. So feel free to try that as well now, later, reach out to us. But yeah, that could be the main thing. And I hope there are no questions, but we are around.
You've now seen what this can look like in this very controlled environment. In the notebook, you've walked through it, but now what I'm going to demo is how it can look like on the cluster and how it, and I'm trying to give you a feel for how this could look like in production.
So funny.
And what we're going to do is we're going to start with a script from the internet. Just going to download a pipeline there and integrate NEPs on that script.
What the
Cool. So now you can see what I'm doing. And let's have a look at the script that we chose. This is some PyTorch Lightning example. It's a transformer pipeline. I'm picking PyTorch Lightning because I'm kind of familiar with it. A lot of deep learners are using PyTorch Lightning. And well, it does make things easy in general. You don't need to understand the deep learning code necessarily, or PyTorch Lightning even. But yeah, essentially there's this PyTorch Lightning module. It creates a transformer model, and then it has methods to create the training step, validation step, test step. It configures an optimizer, and it has like this main function. And the HDMI cable is a bit jittery, but I hope you can still follow. So what I'm going to do is I'm going to download the script. And I'm connected here with our cluster because we do want to run this on the GPU eventually. What could ever go wrong? And yeah, I pre-downloaded the data for us, but otherwise this folder is empty. The script actually takes care of the data loading. It's just for us to save some time. So yeah, let's download the script. It's already downloaded. Have a look what this looks like. And yeah, I'm also not really a Vim user, but on the cluster I need to use Vim. I'm going to commit all the cardinal sins of Vim, but I hope you'll excuse myself. Excuse me for that. So yeah, there's this pipeline. We need to install the requirements. I also installed them to save us a bit of time. It's just a NAPS library, PyTorch Lightning, and requests to download the data. Not going to execute that now. But yeah, let's check briefly if the pipeline is actually running. If not, that wouldn't be good. It will need some time, especially for the first time. It needs to initialize the caches and stuff like that. But oh yeah, it's already running. Great. And I'm not going to let this run through because it takes a lot of time. But yeah, the pipeline is running. And to make things faster, to get to the point where we run naps, I'm going to use this little feature from PyTorch Lightning that's pretty nice, where I can say, this is just a dev run. It basically subsamples the data for me and handles all of that. That's just PyTorch Lightning. And I'm also going to increase the batch size a bit, just to make things a bit faster too. Cool. So let's see if things are still running. This is really annoying. But yeah, it is still running. Cool. So let's get to integrating naps into all of this. First, my imports. Just importing naps and logging as that's needed. And I'm also going to configure logging so we see what's going to run here. This is all just basic Python stuff, right? Setting it all to info. And we're now going to run through the 3 steps that we need to run naps. The first one just being to create the run pipeline function. And I'm just going to use the main function that's already there. And what I have to do is I have to parameterize it to take the learning rate into account, because all I'm going to do is I'm just going to tune the learning rate here. I'm going to expose the hyperparameter. I'm going to start with the main function here, set it to its default. Then I'm going to pass it to the model because that's where the learning rate is used in PyTorch Lightning. And I'm going up. That's where I'm passing it to, exposing that here as well. And setting the learning rate like this. And it needs to connect to the optimizer in the end, right? So this is what I want to parameterize in the end. All right, but that's not all we need to do for the run pipeline function. We also need to return a loss in the end. And for that, I don't actually care about the test accuracy. I care about the validation accuracy. And I always have to look this up, but now I remembered how to do this with PyTorch Lightning. We have all the metrics collected in this dictionary here, and I can just say I take the val loss, which is essentially the thing that's being logged in this line here. Yeah. Okay, so with the run pipeline function set up, let's see if it also works. Yep, it still runs through, but it's not running a naps run yet. So the next thing we have to do is, of course, create the search space of things. And for that, that's step 2. And for that, we create a pipeline space. And you've seen this already in the notebook. All I need to do is create this dictionary, say it's a float parameter, and give it some bounds. And I'm also giving it its default already, so we can make use of the prior set there. I have no idea if this default is actually reasonable, but nice thing, our algorithms can recover from bad defaults. And lastly, I need to create the run call. And pass all the necessary arguments, which is just the run pipeline function, where we here now modified the main function. We give it the pipeline space, of course. And the root directory always have to specify. And give it some budget to work with. So, and this should already do the job and run BO and things. Let's see if it works.
It's a bit artificial this HTML part. So shakes. You can do it.
Yeah, things are not crashing. That's a good sign. And as you can see, we're already evaluating all the configs. Oh. It seems to be a projector issue. Nothing we can do about it, sadly. We did test it before, but yeah. Not the live demo that's failing, but the HDMI connection. Oh well. All right. So we have the Naps run working here. And now we still want to add fidelity optimization into the picture. And yeah, as you've seen, all we need to do more or less is add an additional parameter. I'm only going up to 3 for the demo purposes now, and I also have to tell it that it's a fidelity. And I also want to change the root directory because I'm doing a new run here, right? Bring it with fidelity. Let's see if things still run. Oh, they probably won't run because I haven't parameterized the main function yet. But let's see it failing for a second. Yeah, it's failing as expected, but we know how to fix it. I haven't actually exposed this parameter in the main function. And I, of course, also have to tell the PyTorch Lightning trainer to use this epoch value. So to not continue this failed run, I have to remove the directory as well. Something I might run into 2. And now things should work, hopefully. Now you see, if you were quick, you saw it's running prior band again, and yeah, it does seem to work. So already we're running with priors and fidelity. I took some code off the internet. It's running, and next thing is I'm going to parallelize it. There's more I could do, like loading the checkpoints, but we're running a bit short on time, so I'm skipping that part of it, just to show off the parallelization aspect of things. And to show that off, I'm spawning some additional terminals, which you can't see right now, but they are there. And all I have to do is first connect me with a GPU, of course. in this additional terminal. It will take a second. The environment is already active. I'm in the right folder. But now I want some more evaluations. And I'm actually just going to continue. Oh no, I'm going to now not run in dev mode for now. Change the fast dev run here. And spawn a worker.
This is for you guys.
Hmm?
This is for you guys.
Yeah, but I'm still keeping it at free. We don't have time to watch it go anyways, but like that I planned anyways. So yeah, this worker is now going. I have another worker up here where I'm also going to spawn something now. As you see, same command, same script, same everything. I'm just going to spawn it up and it should all run and work. And you see it starts with config1. So yeah, it indeed does work. I'm going to another, I'm on the login node of the cluster here, and we can see that this run is going on. We're at the third config already. We see what's happening here. And yeah, now we could just watch the run. We could spawn additional workers. Yeah, there's the hand raised.
You use hardware as a requirement. So as I transformers, and what you did iterate here process, and you did that very energies.
Yeah, so what we do for that's a very good question. We have an example, not showing exactly this, but the technique that you would use to do this, and what you would use to do this. If I manage to navigate to examples, you would use your run pipeline function to construct a Slurm script for you, because then you can take the hyperparameters into account and calculate, for example, for this specific hyperparameter setting, I need 100 GPUs. And then you can, in this Slurm script that you're constructing, you can just, parameterize the number of GPUs according to your calculations. And then Nevs will take care and spawn this Slurm script for you. And yeah, you're essentially free to do all sorts of things there. Thanks. So yeah, this is all going on. I think I hope you're convinced that we can parallelize easily. Let's finish the talk quickly. I think we skipped this part. Yeah, and just go through the takeaways. As you've seen,
Like a level show.
yeah, Frank will talk about it in more detail and better anyway, so we don't need it. Yeah, we have HPO algorithms tailored to deep learning right from the get-go. They work with really minimal resource requirements. Think 5 full trainings or even like 2 parallel trainings with 2 of them sequential, something like that. We make all our algorithms available as we develop them. And every technical choice that we face alongside our journey, we make in favor of deep learning. Yeah, thanks.